Welcome to today's episode, where we're diving into the fascinating world of batch processing and distributed data systems. If you've ever been curious about how massive data sets are processed efficiently, or how algorithms are executed on such a grand scale, you're in the right place. We'll be exploring key concepts, tools, and techniques that make all of this possible, including Spark, Flink, and the evolution of data processing since the early days of MapReduce. So, grab your headphones and let's get started. To kick things off, let's talk about how data is managed in distributed systems. Two major players in this arena are Spark and Flink. Spark uses something called Resilient Distributed Datasets, or RDDs, which help track the lineage of data through its transformations. This means that if something goes wrong, Spark can recompute lost data based on its history. Flink, on the other hand, takes a different approach by checkpointing the state of operators, which allows it to pick up right where it left off in case of a failure. Now, when we discuss recomputing data, a critical question arises. Is the computation deterministic? In simpler terms, if you run the same input data through an operator multiple times, will you always get the same output? This is crucial because if some data has already been sent to downstream operators and we need to restart, discrepancies can create chaos. A common solution is to restart the downstream operators as well, ensuring consistency across the board. To avoid these cascading faults, it's essential to design operators that are deterministic. However, achieving determinism can be tricky. For example, many programming languages don't guarantee order when iterating over hash tables, and algorithms that use random numbers or system clocks introduce non-determinism. One way to combat this is by generating pseudo-random numbers with a fixed seed, which ensures consistent outputs. Let's shift our focus to the architecture of data processing. Traditional batch processing often involves writing intermediate results to temporary files, while modern data flow engines like Flink adopt a more streamlined approach. Flink emphasizes pipelined execution, meaning it can start processing data as soon as it receives it, rather than waiting for the entire input to be ready. This represents a significant improvement over the traditional MapReduce model, which requires complete input before any output can be generated. Now, when we look at graph processing, we encounter a different set of challenges. Graph algorithms often require analyzing relationships between data points, which can be complex and iterative. Take the famous PageRank algorithm, for instance, which assesses the popularity of web pages based on their links. Traditional MapReduce struggles with these iterative processes since it reads the entire dataset for each pass, which can be quite inefficient. To tackle this, the Bulk Synchronous Parallel or BSP model has gained traction. This model, implemented by frameworks like Apache Giraffe and Spark's GraphX, allows for iterative processing of graphs. In the BSP model, vertices can send messages to each other, and the state is maintained across iterations, leading to more efficient computations. Unlike MapReduce, which processes everything in one go, BSP can focus on changes and only process new incoming messages. Let's discuss communication between vertices in a graph. In the Pregel model, which is a variant of the BSP model, vertices communicate through message passing instead of direct queries. This design enhances performance by reducing waiting times and ensuring that all messages from one iteration are processed before moving on to the next. The framework guarantees that messages are delivered exactly once, simplifying the programming model for developers. However, graph processing in a distributed environment comes with its own set of challenges. If the graph is too large to fit into memory on a single machine, distributed processing becomes necessary. Yet, this often leads to increased communication overhead, as messages between nodes can sometimes be larger than the original graph itself. In many situations, if a graph can fit into memory on one machine. A single-threaded algorithm might actually outperform a distributed one. As we reflect on the evolution of distributed batch processing, it's clear that execution engines have matured significantly since the introduction of MapReduce. Today, these systems can handle petabytes of data across thousands of machines. With the infrastructure challenges largely addressed, the focus has shifted to improving programming models, enhancing processing efficiency, and expanding the range of problems these technologies can tackle. This is where higher-level languages and APIs come into play. Tools like Hive, Pig, and Cascading emerge to simplify the process of writing MapReduce jobs, which can be quite labor-intensive. As newer engines like Tez and Flink developed, they offered compatibility with these high-level languages, allowing users to transition without needing to rewrite their code. The Dataflow APIs provided by Spark and Flink are designed to express computations in a relational style, making it easier to join datasets, filter data, and aggregate results. This not only boosts productivity, but also enhances execution efficiency at the machine level. Moreover, these modern frameworks support interactive use, enabling data scientists and analysts to write and run analysis code incrementally. This approach is particularly beneficial for exploring datasets and experimenting with different processing methods, echoing the Unix philosophy of building small, composable tools. As we wrap up today's episode, it's evident that the landscape of batch processing and distributed data systems has undergone significant transformation. From the foundational concepts of MapReduce to the advanced capabilities of Spark and Flink, the focus has shifted towards efficiency, flexibility, and ease of use. As these technologies continue to evolve, they will undoubtedly unlock new possibilities for data analysis and processing, allowing us to tackle even larger and more complex datasets. Thanks for tuning in. We hope you found this exploration of batch processing and distributed systems enlightening. Until next time, keep questioning, keep exploring, and keep processing.